Okay. So, welcome everyone. Welcome to our first Chemaraderie of 2024. It's good to see everyone back and yeah, looking fresh and looking forward to some good talks this year. So I'd like to start off by acknowledging the traditional custodians of the land we're meeting on today, the Whadjuk Noongar people. And I'd like to acknowledge and respect their continuing culture and contribution they make to the land that we live on. Yes, I'm going to make some notices before we introduce the speaker. Got quite a few things going on this year. So yeah, this year we're actually being sponsored by the Chem Centre for all of our Chemaraderies. So that's going to enable us to have some extra catering every month that we have this. So that's going to be good. This month's going to be by Lament. So we'll be having that after the speaker. So yeah, it's really nice for them to sponsor us. So next Chemaraderie is going to be in April because we have the Bayliss lecture in March. And in April, we're going to have Adam Martin. You might remember this face. He was on the industrial panel discussion that we had in October. He discussed a desire to be able to present what he does as well and discuss what he does at PYC Therapeutics. Next, on the 27th of February, we've got the OPAC Global Women's Breakfast. So this is open for registration for everyone. A lot of people get a bit, not concerned, but confused because it's a women's breakfast. They think men can't go, but men, we're welcome to go. So please register. It's going to be at the Colliers Golf Course. So yeah, please register for that one. And there's also going to be a Super Golf event, which is going to be on Saturday, March the 16th. And that's at Henley Brook. I don't know if anyone's done Super Golf before. You don't have to be good at golf for this one. It's a nice big ball and plastic clubs, so you can smash it around the course and not be too embarrassed by losing your little white balls in the trees like I always do. So please, register for that one. So the reason we're all here today is to see Professor Honky Sun present. He's from the discipline of chemistry at the School of Molecular Sciences at UWA. And he started off in 2009 to 2016 at Curtin before he moved on to ECU, where he became an associate professor and professor in chemical engineering. So currently he's on the board of the ARC College of Experts. He's a delegate to the Australia-USA Hydrogen Research Partnership and board director of Minerals Research Institute of Western Australia, or MIRWA. Also, he serves as editor-in-chief for Cleaner Chemical Engineering and associate editor for RSC Advances. So one of the main reasons we got him to come and give a talk today, not just because of his excellent research, but he was also awarded the WA Mid-Career Scientist of the Year 2023 Scientists Premier Science Awards. So yeah, I thought it's an excellent opportunity for him to come and give us a talk. So please welcome our speaker.
Thank you very much. Should I?
Yeah, take that one if it's easier for you. So I should clip onto you. Here we go. Turn it around that way. Okay, that's fine in there. Wrong button. There you go.
Thank you very much, Terry. Good evening, everyone. Thank you very much for joining this event. My name is Hong Chi-Sung from UWA. Today I'm going to talk about the role of catalysis for solid to hydrogen conversion, mainly for heterogeneous catalysis, not the very popular electrolysis. Now everyone is talking about green hydrogen. In 2022, federal government provided the funding to CSIRO to support international hydrogen research partnerships. And I was fortunate to join the delegation to Australia-US Hydrogen Research Partnerships in October 2022. We went to America to attend the Hydrogen Americas Summit, and also we visit Australia's US Embassy and a number of very famous labs. For instance, we visited this lab, and there's solar panel. It's pretty much a demonstration for everything about the green hydrogen, like the production of renewable energy, that is to power the electrolyzer to produce hydrogen. Then they did the compression and the storage, and also build up the hydrogen refuel station. It's pretty much the petrol station, and they're like hydrogen-powered vehicles. You can add the hydrogen there. And also from that visit, I realized globally, there are so many government driving forces and strategies to promote green hydrogen. For example, US has hydrogen shot that was launched in June 2021. The target is to reduce the cost of clean hydrogen by 80% to $1 per 1 kilogram of hydrogen in 1 decade. Australia, even further, earlier, like 2019, we had a national hydrogen strategy, and now federal government is reviewing the strategy and to ensure we're on the right path to be a global hydrogen player. Also, EU has, 2020, has strategy, policy, action points in 5 areas, and also China in March 2022. That are long-term plan for hydrogen, covered 2021 to 2035. I think there are great evidences globally green hydrogen is being heavily promoted. That is a recent story, but the hydrogen definitely has a very long story. In 1776, hydrogen was discovered by a British scientist. That was leading to the discovery of that water is made of hydrogen and oxygen. We can produce hydrogen from water, and after the consumption, the product is water. That's like a dream. You have infinite energy resource from water. In 18,000, electrolysis was discovered, still very long time ago. And in 1839, 38, fuel cell effect was discovered. That is about the whole story we are talking now, how to produce green hydrogen by electrolysis. Then we convert that, use fuel cell to convert that to electricity to power EVs, electronic devices. And of course, there are more historical stories about the hydrogen. In history, there are a few times hydrogen have been strengthened, just like what we are doing now. It's in 1972, the hydrogen economy was first coined. And at that time, there was a war. In 1990s, the world's first solar-powered hydrogen production plant was built. And also US launched a 5-year management and implementation plan for hydrogen research. At that time, there was a war. Very recently, we can see the global hydrogen strategies. because there is a war, or there are wars around. This from the public data. From 1975 to 2018, over about over 40 years. The global demand for pure hydrogen is like this. This one is for like this for ammonia refineries, for others. Below 20 and over 40 years is about below 80 million tons. We can see the increase, but the gap acceleration is not that big. It's about like 4 times higher. And now it is the prediction, 2020 to 2030. Now, here is every 5 years, here is like every year. We can see the huge jump. In 2021, $1.8 billion. Now it is predicted that in 2030, $90 billion. We know that one is a fact. This is a prediction. We will see if the prediction is true or not. So the reason for hydrogen or green hydrogen, because it does not add carbon emissions to atmosphere, but greenhouse gas effect has been long known for everyone, and also we know the pressure for climate change. But sometimes you see the rise of hydrogen, sometimes it's cold. So my personal understanding, the supply chain of the energy crisis probably is more the reason than climate change. Of course, that is a controversial point. But many of us know hydrogen has different colors. Of course, we are after green hydrogen. The color is depending on the source of energy, source of hydrogen, and the production process, and also the CO2 emissions. What we are after green hydrogen, the energy should be provided by renewable energy. And the source is water, and the process is electrolysis, and there's no CO2 emission. Of course, there's others, orange, pink, red, yellow, from solar, that could be part of green hydrogen, because solar also renewable energy, and also others. We see gray and blue. Actually, at the moment, steam methane reforming is still the main player for producing a global hydrogen. And of course, that has CO2 emissions. And if you do some CO2 capture and storage, that becomes blue hydrogen. As I mentioned before, electrolysis has a very long history. It is meaning like electrochemistry here. I don't want to go too many details. There's a membrane called the protein exchange membrane. There's a cathode, anode, and with water, with the current, it produces hydrogen and oxygen. I actually checked from Amazon. We can actually buy an electrolyzer to produce hydrogen as you want, and that's not expensive. And from my understanding, like the theory is not new. It's already in high school chemistry textbook, and it is not advanced technology. So the feasibility is good. If you want to launch a project, then you can. And there's no emission with the pressure of climate change. Everyone loves like the green hydrogen, because no emission. After the fuel cell, it becomes water, and you use water to produce hydrogen. It's like a perfect cycle. And also it can be probably, most likely, the reason like we are pursuing a rise of green hydrogen is it can be energy carrier, because that can de-risk the energy crisis. and also the like de-risking the fossil fuel supply chain. Australia is in the position to like promote green hydrogen because that is economic benefit from export to Japan and Korea. So I think that's the driving force. The electrolyzer has anode and cathode electrode materials that can be like platinum, but that's too expensive. So we use transition metal-based electrocatalysts to lower the overpotential to make like the process easier and also less energy intensive. This is not my field, but I know in HER and OER, in both fields, there have been overwhelmingly like increasing efforts in the area, mainly for the development of catalysts. For HER, also for lowering the overpotential platinum group metal-based catalysts have been developed, and also for oxygen evolution reaction, OER. A large number of materials have been tested as the catalyst for like lowering the overpotential for promoting HER or OER. So some other considerations for green hydrogen. Currently, the price about $5 to $6 per kilo hydrogen. Green hydrogen, we use renewable energy. For example, we use solar panel to convert solar energy to electricity. Pretty much the solar panel can have like energy efficiency 20%. When we convert solar energy to electricity, that is to drive electrolysis to produce green hydrogen. At that step, the efficiency is about 70%. Then from green hydrogen to power fuel cell to generate electricity, another 6% energy efficiency. If you use green hydrogen to power like a combustion engine, the efficiency is about 40%. So if we look at the utilization efficiency of renewable energy from beginning to the last step, even from the solar panel, green hydrogen, the fuel cell, the overall energy efficiency is 8.4%. And there are some other costs associated with the process, like the manufacture and the disposal of solar panels, or if that is from wind engine to manufacture that, to dispose maintenance, also the cost of electrolyzer, electrocatalyst, fuel cells, etc. Of course, like the techno-economic analysis or life cycle assessment is not my field. That also has compression, storage, and transport. I know we have several experts about the storage. So if you look at the process, we have electricity here. Looks like you can directly go from renewable energy to electronic devices or EVs with energy storage systems. So that's why sometimes I'm confused. What's the role of green hydrogen? There's green hydrogen. The price is like $1 or $2 per 1 kg hydrogen. That's the most commercially available technology to produce large-scale production of hydrogen. Use steam methane reforming methane with water at 8 to 900 degrees and some pressure to produce syngas, which has carbon monoxide and hydrogen. Of course, that use nickel-based catalyst. If you want to have more hydrogen, you can use water gas shift reaction to convert carbon monoxide with water to produce hydrogen. Of course, that process releases CO2. That's the main point why that is called gray hydrogen, because that's carbon emission. From that process, of course, if we produce 1 kilo hydrogen, that process has 5.5 kg of carbon dioxide. And with the overall other energy inputs, it's like you produce 1 kilogram of hydrogen, that releases 10 kilograms CO2. That's why people think that's better, right? But you can also think if you use methane just as a fuel to combust, that burning same amount methane that release same amount CO2, 1 mole, and at the same time it produces like 4 moles of hydrogen, and over 20 years period, methane has 80 times more potent at warming than carbon dioxide. There's another way, convert methane with CO2, a greenhouse gas, like 2 greenhouse gases to syngas, to carbon monoxide and hydrogen. That can be like a syngas feedstock to produce fine chemicals, or can be directly as a fuel. Of course, this process is at an early stage for commercialization. We talk about renewable energy. It can be from wind, geothermal, water, or biomass. It can also from, like most famous, from solar energy, solar panels. Because solar energy is abundant, clean, sustainable. It provides much energy than we need, actually, but we just cannot efficiently harvest the solar energy. Sunlight depends on different wavelengths. Below 400 nanometers, it is UV. The photon energy is strongest of like all others, but the UV just represents 4% of raw solar energy. Between 400 to 750 nanometers, there's visible light, that some light we can see. The photon energy is moderate, and also that has over 40% of raw solar energy. Infrared, pretty much the photon energy is low, and it's about the thermal effect. So solar energy has many different utilization methods. Photosynthesis is the natural process. That is the way to grow plants and biomass. Solar thermal, like we use that for sun drying or solar heating, solar heater of the roof. Photovoltaic, let's use solar panels or solar cells to generate electricity. The process is not exactly a physical process, but you convert light to electricity overall. That seems like a physical process. Photocatalysis is actually a chemical process that can be used for energy and the environment. So it's like photocatalytic water splitting, having the potential to be another type of green or yellow hydrogen. Direct solar-driven photocatalytic water splitting, at the moment, based on the progress, the price is about 18 to 20 US dollars per kg of hydrogen. And the commercial target, like we need to increase the solid to hydrogen efficiency to 5 to 10%. And as I mentioned before, if we use solar panel, electrolysis, fuel cell, the overall efficiency about 8% efficiency. And a typical photocatalytic process that requires a semiconductor, for example, titanium dioxide, that has a band gap energy 3.2. It has, we have physics people here, that has a conduction band, valence band. If the photon energy is greater than the band gap energy, then electrons will be activated from valence band to conduction band. That is activation process. The photo-induced electron hole pairs will be transferring to surface, but that will be via separation and the recombination process. If the electrons and holes are successfully reaching the surface of a catalyst particle, there will be surface reactions. Again, that has a long story and history. In 1972, it was discovered photocatalytic splitting to produce hydrogen. And also in 1970s, the degradation by photocatalysis or CO2 reduction by photocatalysis was discovered. In that area, playing with the photocatalyst materials, a large number, just like HER, OER, a large number of materials have been used as photocatalysts, like metal oxides, metal sulfides, nitrides, complex plasmatic metals, or metal-free materials. The most popular is titanium dioxide, but that can only respond to UV. That's why we developed a lot of modification methods. And we also look at metal-free carbon nitride as a photocatalyst because that can respond to visible light. But the solid to hydrogen conversions should also consider reaction systems, like the rules to utilize solar energy. The catalyst materials, which should be considering the cost, activity, selectivity, and stability. Also the catalytic processes. It can be photocatalysis, thermocatalysis, electrocatalysis, or some novel integrated catalysis. And also, if you want to make that scalable, we need appropriate reactor design. There can be batch or flow reactor, what kind of phase we need, what kind of light, temperature, or pressure we want to include them for the operation conditions. I have a book edited by me for solid to chemical conversion that includes a range of different processes for how to utilize sunlight, like sunlight with water, biomass, natural gas, carbon dioxide, or nitrogen. That's different catalytic processes for utilizing solar energy. But back to hydrogen, if we just look at the solar-assisted hydrogen generation, that can be still in various reactions, like water splitting. We can disperse particles in water with sunlight irradiation. We can produce hydrogen. That doesn't need to convert to electricity and electrolyzer. We can also use, a steam reforming of methane was maintained by thermocatalysis, but we can also make that workable under sunlight. Use sunlight to drive steam reforming of methane or dry reforming of methane to produce hydrogen, 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 or water gas shift reaction. So most of chemical reactions which were operated with thermocatalysis at a temperature, and the temperature has to be sustained by external energy inputs, and the reactions can be actually carried out on the sunlight. Here's an example. We use carbon nitride as a metal-free photocatalyst, but that was modified with one-dimensional carbon nanotubes. We use melamine and a single-wall carbon nanotube to prepare a single-wall carbon nanotube modified carbon nitride. If we use another thermal etching process, we can have field-layered carbon nitride modified with single-wall carbon nanotube. We can use TM image, look at the morphology structure of different materials. This is bulk carbon nitride, and this is ultra-thin carbon nitride, single-wall carbon nanotubes, and high-resolution carbon nanotubes. For the materials, we have carbon nitride and nanotube. If we use FM, we can look at the thickness of the layer, just 2.7 nanometer for like the thickness. The idea is like that. We have the materials we loaded with platinum and ruthenium as the co-catalyst. Then with the light, we can conduct water splitting to produce hydrogen and oxygen. Here's the efficiency. We compare carbon nitride and also the materials we developed. We can succeed in the overall water splitting, and apparently the performance is much higher than the carbon nitride without the modification. If we use like this chemical to consume the host, then we can significantly increase the hydrogen evolution rate. Now here, like 3 hours, 4 hours, we have like about 200. With the sacrificial agent, we can significantly increase to about 3,500 or 4,000. And we compare different materials. We can see the efficiency, how to improve the efficiency. The material, the semiconductor, has an absorption spectrum, and at a certain, if we conduct the water splitting at a certain wavelength of light, we can measure the amount of hydrogen and also calculate the photons received by the system, so that we can calculate the quantum efficiency. At like 420, the quantum efficiency at a certain wavelength is about 8%. And if that increase to visible light, the quantum efficiency will be reduced significantly. This is not like the 5 to 10 solid to hydrogen efficiency. This is just the quantum efficiency at a certain wavelength. When the hybrid has interface, the interface leads to the decay of charge carriers. We also use melamine and sodium bicarbonate to produce porous carbon nitride. That is because with thermal decomposition of sodium bicarbonate, it produces carbon dioxide. Carbon dioxide can create pores for the carbon nitride. If we apply hydrogen reduction, we can actually, within the pores, we can fabricate graphene. So we have carbon nitride pores fixed by graphene that can like enhance the efficiency. This for the selective oxidation of a chemical. That's not the topic of today, but we can compare the different materials for hydrogen production. Also, we compare the absorbance. That's like the absorbance to the different wavelengths of the light. That's from UV to visible region. Based on the UV absorption spectra, and we can also calculate the quantum efficiency at the different wavelengths. With that material, the carbon nitride is a semiconductor with the graphene. Graphene is considered as a zero bandgap semiconductor. So that can be a co-catalyst to capture electrons from the system to increase the efficiency. This is a paper from Nature, not from me. That's kind of like a large-scale test for photocatalytic water splitting. The overall area 100 square meters reactor. Of course, that's like combine many different reactors together that use a photocatalyst then to collect oxygen, hydrogen from different reactors. 1,600 panel reactor units, and the overall hydrogen and oxygen is separated here in the box. But that was published in 2021. The solid to hydrogen efficiency only 0.76%. Even with the visible light, just 1%. The target 5 to 10%. Another paper from Nature, again not from me, that use a very complex and expensive material as the photocatalyst. Then, with reaction with tap water or simulated seawater, and also outside the natural sunlight test, it can achieve a solid to hydrogen efficiency of 9.2. What we want to note here is that the temperature is 70 degrees. That utilize like the photon energy and the thermal effect. That's why we want to pursue photothermal catalysis, because again, this is solar energy distribution. This part is just UV, the photon energy is high, but the overall energy is very small, and the visible light like here. For most photocatalytic reactions, we can only utilize UV, very little part of visible, and we cannot use infrared, the thermal effect. So we want to promote photothermal catalysis. That has different categories. Like for the thermal-dominated photothermal catalysis, the driving force is thermal energy, and the role of hot carriers, like the photon energy, or the role of photons, is to improve the selectivity. Of course, that use different catalyst as the different material as the catalyst. There can be also charge and thermal coupling for the thermal catalysis, driving force of thermal energy or the carriers and their interactions. If like the charge dominates the process, that the driving force will be changed to the hot carriers, then the role of thermal is improve the charge dynamics and also sustain the reaction temperature. Of course, the fundamentals is complex. That includes excitation, how to produce the electrons holes pairs from like a semiconductor or plasmonic metal. And also there's limitations, like for a semiconductor, the position of conduction band or valence band that will determine if the charges can be transferred to the reactants molecules, and also based on if there's an interface or heterojunction with metal or semiconductor, the electrons could or cannot be injected to semiconductor to participate the reactions. Also, if the metal, plasmonic metal, that has the charges, but also there can be or cannot be injected into the adsorbents to drive the reactions. Of course, for the plasmonic metal, the surface plasmonic resonance state can be like back to with the relaxation, then the that will be producing thermal effect. For the semiconductor, conduction band and valence band, the charges can be produced, but if they are not participating in chemical reactions, they will undergo the recombination. The recombination will release heat. And also, if that is for carbon material or organic materials, that will also absorb energy, but with the lattice relaxation, that will directly produce heat to increase the temperature. That's the origin of like photothermal catalysis, like the origin of heat. We have investigated photothermal catalysis for the dry reforming of methane. This is thermal catalysis. We use like the nickel and cobalt alloy supported by silicon. This study is just like a thermal catalysis. We compare the efficiency for generation rate for hydrogen and carbon monoxide. Actually, the alloy doesn't perform better than nickel only. Like nickel catalyst show the highest conversion efficiency. We also have the drift spectra to find out the reaction intermediate, also use computational studies to investigate the activation of methane, activation of CO2 on the alloy, and use computational studies to find out the CO2 absorption energy, CO desorption energy. But for the thermal catalysis, actually the catalyst is not better than nickel only. But for photothermal catalysis, we carry out reactions at the room temperature 300 degrees, 500 degrees, 700 degrees, and use a range of catalysts like a cobalt. This one is nickel. Then we put nickel into cobalt, increase the nickel percentage. Then we find out the newly developed catalysts show better performance in photothermal catalysis than the nickel only. We compared a photocatalytic without the temperature about the different materials. The alloy show a better performance than nickel, and we also calculate the photo contribution to the photothermal catalysis for dry reforming of methane, and also the alloy is better than nickel only. We investigated the effect of light intensity and the wavelength. We calculated the quantum efficiency at 700 degrees. For room temperature, the quantum efficiency at a certain wavelength, just 5, 6, 8. But in that photothermal catalysis, the quantum efficiency can be above 60%. Like 60% of photons can be utilized for chemical reactions. We also compare the photothermal catalysis with light. If there's no light, that's just thermal catalysis. We can see the big difference. We also compare like the stability to run 12 runs. The stability is good. For another titanium dioxide loaded platinum photocatalysis, for the same photothermal catalyst, we compare dry reforming of methane, also find out, use electron paramagnetic resonance to check out with the dark and light, the concentration of hot electrons at room temperature 100 degrees, 300 degrees. We also check the lifetime of carriers. We find out the effect of temperature on the lifetime of carriers and also the concentration. We compare two dry refilling of methane, also CO2 reduction with hydrogen. Find out with increasing the temperature, the turnover frequency, like has an optimum temperature, then decrease, but the hydrogen to carbon monoxide ratio is increasing. And again, the enhancement with hot carriers have that has like optimum temperature. Like different reactions has a different reaction mechanism. We also compare like the quantum efficiency for different reactions at a different temperature. The quantum efficiency apparently like much higher than that for like conventional photocatalysis, and we demonstrate DIM and also CO2 reduction. We demonstrate like the excellent stability for photothermal catalysis. For the same photocatalyst, we can like fabricate the catalyst at like 3.6 nanometer for two different supports, titanium dioxide and alumina. We can like have the same, almost identical platinum nanoparticles on the spots, so we can compare the effect of spots. We use like computational study to find the active size of the different materials, even with different spots in photothermal catalysis. For photocatalysis, if that is at a room temperature, so that is very easy, room temperature ambient pressure with the light, so that can be liquid phase or gas phase. For photothermal reactions, that's very difficult. And now it's like fundamental stage, we need to provide a light and sustain the reaction temperature. So for practical applications, we probably need like a solder concentrator to sustain the reaction temperature and also provide enough photons. I have a current project that is for ARC discovery, that is to produce hydrogen actually from ammonia. For that project, ammonia is used as like an energy carrier. Then we can store and transport ammonia then on site to produce hydrogen from ammonia. For future projects or my current research interests, I'm looking into the photothermal catalytic dry reforming of methane that can use like natural gas, which is very abundant in Western Australia, then with carbon dioxide to produce syngas. Syngas can be directly used as a fuel, and it can be used for feedstock to produce fine chemicals. Of course, if you want, they can also use to produce pure hydrogen, and also like for the steam reforming of methane to produce hydrogen. I think that also has like a future for practical use of solar energy, because that don't need to like multiple steps to convert. Conclusion, hydrogen, everyone is knowing that solar energy can be converted to hydrogen by different ways. So we need catalyst design, we need like a reactor design, we need to choose different reactors. So with above efforts, we may lead it to the practical applications of all the studies. At last, I would like to acknowledge I was working initially at Curtin University, then I moved to ECU. Now I'm working at UWA, and also a project has been supported by ARC. At last, thank you very much for joining this session. Thank you very much.
Brilliant. Thank you very much for your talk. We've got time for a few questions. I've got any? No? I've got one for you. I like that new project that you've got going on there with the ammonia splitting.
Yeah.
Obviously, that's going to be an important process with hydrogen export and everything. There's a lot of companies looking at using ammonia to transport overseas. And what's your efficiency on this so far?
This is a new project that just granted.
Course,
We have recently published a paper. The efficiency is still very low because we use film, but in the new project we are trying to use it's kind of like a fluidized bed reactor, that fundamental research that can be driven by sunlight. And with a fluidized reactor, we have particles, catalyst particles, we call the ultralight photocatalyst, so that it can split ammonia to hydrogen and nitrogen. So that's the idea, because from my understanding, ammonia storage and transport is much easier than hydrogen. So,
yeah, definitely. You know, there's already boats made up for that type of thing and everything. But yeah, any back?
Thank you. It's a nice presentation. Have you ever tried some metal oxides for the catalytic reactions on solar systems? Because I saw some graphenes and carbon nitrides. Have you ever tried metal oxides?
No, we haven't tried to use that material, because for the photothermal catalysis, normally we can operate like 500 degree to 700 degree. For carbon nitride, that is metal-free material. It's like polymer, so that's not stable for like that reaction condition. We have tried silica-supported nickel or cobalt or alloys for the photothermal catalysis, and then we also tried like the titanium dioxide supported platinum. We don't think carbon nitride is suitable for photothermal catalysis.
I've got one more question for you. From your from the early work that you presented on here with the carbon nitride sheets and everything as a catalyst, are these like commercially available, or do people synthesize those in the lab, or how do people get hold of those?
Yeah, we don't have industrial project for that, but that can be commercially available, because like the precursor is a very cheap chemical melamine, and that can be massively produced with a very feasible condition, like thermal condensation at 550 degree in a muffle furnace. And if we want to make the bulk structure exfoliated to ultra-thin layers, we can just conduct another air thermal etching process to have the ultra-thin layers. So if we want to produce like at a large amount, that can be done.
Sounds a pretty complicated process though. But yeah. Okay, any other questions? If not, I'd like to thank the speaker again. We've got a little gift for you.
Thank you so much.
And I'd also like to thank the Chem Centre for sponsoring the event. And please enjoy the food outside. But let's thank Honky again.
Thank you.
That's really interesting. Brilliant.
Yeah, I think once I talk to the
Yeah, I think it definitely covered the beginning. It's a very broad introduction, so definitely give a lot of broad insight to people. And then, but by the end, he was able to give a lot of insight. So other people that are more interested in the field would find that more interesting. And so the lady back there, she's just finished her PhD, and she was doing fantastic work as well. So yeah.
Thank you so much.
Hit them up.
Thank you so much.
Thank you so much. Please, stick around, chat to some people, and enjoy some food. And we'll delete your.
I can make sure I delete my file.
That's it. Yeah, I've got it. Yeah, brilliant.
Yeah.
No, thank you so much
Thank you.
It's always good to get different speakers to come in and. Especially when it's all about renewable energy. Everyone gets at the moment.